So hi everyone, I'm Timothée Verdier. I'm a senior developer in the machine learning team for Wolfram Research. And I'm glad to welcome you here for this talk about how we integrate large language model, like LLM, in our technology stack, especially how to create, build, and evaluate workflow, agentic workflow using the LLM in the Wolfram language. So let's start with a small detour so that we're all on the same page. I'm sure you've heard about neural networks, but very basic introduction, because this is a state-of-the-art algorithm underneath language models, and it's always good to know the backend to understand what's going on. So neural networks are basically a family of mathematical functions that you can tune in order to train it and to learn features. They are bio-inspired by the way brain works, by integrating based on neurons, which integrate the information from their surroundings, with basically weighting the inputs compared to a given threshold, and firing or not to the following cells. And the idea is to repeat those very simple mathematical model over and over again to produce very rich and powerful mathematical function. In order to perform this computation, you need to encode all the data as numbers, and this is arbitrary, but you have canonical and natural way to do it. For instance, to just give the value of the alpha channels for the pixel of an image, red, green, blue, or if you have a string, you can just chunk the string in whatever level, character, words, anything we eventually call token, and replace them by the indices in a dictionary. And as soon as you have those numbers, then you can just process with a computation every output of at a given stage being input of the next layers of neuron, which takes the value through weighted connection, the value of the preceding neurons, and feed the following layers of neuron with it. And you can organize this connection the way you want in very diverse architecture. And the way you learn, the way you tune those functions, the way you fit the function of interest is by adapting, tuning the connection weights. And I think that's just enough to understand how neural networks are working. And the reason they are very, very broadly used is because they are very powerful. They can express basically any function of interest. They can adapt to very diverse type of inputs. The more data you have, the more, the larger you can grow in depth and weights the network and get a finer approximation for your function. You can use them basically in any type of task, and the values you are learning throughout the training are very rich representation of your data. So nowadays, most language models are built on top of neural networks, and this is basically when we say language model, we mean a function that represents that maps represents the distribution of tokens and express the statistics of written language, be it natural like French or English, formal like Wolfram language, and large refer both to the training data, which are huge corpuses, and the neural network's capacity, basically the numbers of weights. So you train them by taking a large corpus of text and you, out of the corpus, you sample as many sequences of tokens, so basically words, you want, and you train the system, you adjust the weights of your system in order to produce a vectors of probability, which is the distribution of probability for the next token, bumping up the weights of the token you actually see in your corpus. And this way, you hope to converge to the actual probability distribution in your corpus. And after this training, you get something such as generative pre-trained transformer. Transformer is a network architecture, and let's not go into detail. Pretend it's because you trained it, and generative, we're going to see that in a second. So if you feed such transformer like this net model, GPT-2, which is an ancestor of the well-known ChatGPT, I'm sure you all heard of it. If you feed it with the catsat on then it gives you the top probability, which I requested, just the 5-1 over the token dictionary it has. So suggest table, ground, couch, bed, and floor. And how to generate the text out of this distribution? Well, you simply sample, you randomly pick one of those following the distribution. So floor is going to be very frequent, but you can also generate the catsat on the table, the catsat on the ground, following those frequency. And you have one more word, and you carry over this recursive algorithm until you reach a special token, which is end of sequence, and you stop. Right. So the power of it is that as soon as you have learned the distribution, it contains very important semantic information about the language. And that's what's used. Nowadays, we don't use anymore. You don't train locally. You go to server where very huge neural network are hosted, and you submit most of the time your request to external provider. With Wolfram language, you can target the most obvious providers being built in with a request like hi there, using LLM synthesize function and providing the target model in LLM evaluator value. If you have a connection register, it will work straight out of the box. If you don't, it's going to pop up to link to your service provider account, in this case, Anthropic. So if you register if you subscribe to LLM Kit, it will basically enable all the LLM-powered function in the language, and it will give you access to the notebook assistants, which I encourage you to watch the talk later on. So with LLM Kits, as default, LLM Synthesize work directly connecting to Wolfram LLM services, and will provide you with a completion for the catsat on the mats. And as you may already have caught, LLM Synthesize is a core function for every interaction with LLM, and all the rest is built on top of it. You can, one important feature of LLM, which made them prominent in nowadays AI landscape, is the fact that they have been fine-tuned in order to generate texts according to answering requests and execute instruction, which made them very powerful system to solve kind of implicit tasks, such as give me 3 warm colors, which is not very easy to express in programmatic rules. And here they are, and you see that the format was not very specified and is quite freeform. You can obviously specify all the generation options you want, such as the temperature to sample the distribution, the max numbers of tokens before you stop to have a short answer, and also add additional prompts prompt is just like the input, all the text you seed to start generating, and it will just modify the output you get from the LLM accordingly. So there you have RGB specification instead of red, orange, and yellow. You can also, with LLM synthesize, query pre-run properties, such as the prompt that's actually going to be fed to the LLM. Here you have the two parts: the write-only RGB specification per line and give me 3 warm colors. But you can also ask for the usage, because you usually pay by the token. And in this case, it's a call request. So the call is made, and you see that it costed you 48 tokens. In order to, so with that, you can basically achieve anything, but there are several extra useful features that we introduce with LLM function, which makes it more tailored for programmation. First one is, usually you want to reuse your prompts, slightly changing them. So it's a templating capability. If you wrap a template object, such as a string template in LLM function, then you can pass parameters like numbers and type to modify live at runtime the prompt that is sent. And the return value is an LLM function that just works like a function but submits the computation to the LLM. And if we evaluate it with 3 and 1, we're going to say have the same prompt as before and return something significantly closer. But you can also add a second feature, which is interpretability, and saying that what you're expecting it has to be interpreted as a repeating colors. And if you do that, what we now do is we provide the LLM with some extra prompting that gives it an information about the expected format, and hopefully that depends on the LLM ability to cooperate and to follow the format. You either get a failure when you cannot coerce to the interpreted type, or and let's try again, or you get the correct result directly programmatically interpreted for programmatic operations. So that's first thing, templating and interpretation with LLM function. Obviously, it's built on top of LLM synthesize, and you can provide an LLM evaluator option, everything you can provide LLM synthesize. Now, it's so far, LLM has been in charge of just generating all the content of the answer. But what's usually interesting is to delegate the formatting to the LLM and the understanding of your requests. But content, you want to have more control about it. So let's assume we have a function, random color, that can generate random color at will given a parameter n. Then if we wrap this function in LLM tool, we provide access to this function to the LLM. We're going to say to the LLM that it has a function color sample, which is a random color generator. So first is the name and description, and that it needs to provide a parameter n, which is an integer, and then that's what the LLM generates going to be interpreted and fed to random color, and you get an LLM tool out of it. The LLM tool just evaluates like a pure function if you pass the argument. But if you pass it in the LLM configuration, it provides LLM access to it through the prompt, prompting the LLM to actually call it. And you see here that it's calling tool color sample to give me a color per day in the week. So per day in the week is some kind of needs some kind of natural language interpretation. It's not something you compute, but it has called a tool to generate those 7 color, understanding the request. And here they are. You see the formatting is not exactly the same as the one in Wolfram. It's been slightly modified by the LLM. And therefore, you control the generation process of the LLM answer. You can using LLM synthesized completion tool text. You can have a textual representation of the interaction with the LLM. We see that first thing that the LLM does is a tool call for 7 color sample. This is the answer, the textual representation of the answer from the tool, and here is the final completion by the LLM. So the way tool works is by back and forth interaction with the LLM to provide the needed part, and that's on the LLM to decide whether or not to call the tool. But sometimes you know what part of the answer you want to be included, because and you want to coerce, to force the LLM to use them. So this is a mission for LLM prompt generator. And what's it's interesting for is that you can ask basically anything to the LLM. Its job is to generate text based in this on the context you provide. But it's you have to understand it's a neural network. It's a frozen generator, so it has no knowledge of what day we are. It's just generate a text, right? So if you ask to give you today's color, it's gonna decide just randomly on a day, and it gets lucky this time. But if I do it several times, it might evolve and change. And you can basically not trust the answer. It's what we call hallucinating in the field. So if you can provide the right information just by a function like date string, then you want to add that information to the prompt automatically, and it has to be runtime, because that's the time you query the answer of the LLM. And this is LLM prompt generator mission. So if we do that again, it's going to add the current date and time to the prompt, feeding what day are we, and give me the color per day in the week. And you see that hopefully the answer is going to be based on the right element. So today is Wednesday, November 5, 2025, correct? And it picked hopefully Wednesday results here. Convincing. Another, and probably the most useful use case for an prompt generator, is to actually feed information to the LLM, the information you know you're interested in, let it format the answer with classic information retrieval. So semantic search index is a very important person in the LLM prompt generator world. And let's say we're interested in Alice in Wonderland contents. Creating a semantic search index means basically taking a collection of documents or pieces of text, chunk the Alice in Wonderland text in pieces, and then index them in order to be able to query it with other data. This is called semantic search because the similarities that is used is based on the meaning of the text rather than the actual classical, keywords. So if you query this index, newly creating an index with a sport game, the query, and return only the max 3 similar items, we're going to have piece of text that talk about this croquet game that Alice and the Queen played in this Alice in Wonderland story. And you may not see any occurrence of sport or game in those excerpts, so that's quite efficient. And now, if we use the index in an LLM prompt generator as a system prompt in the configuration, it understands that what we're interested in to provide those information to the LLM. So it queries with our LLM synthesize input or LLM function input the index live at runtime, and you see that the answer is based on the excerpt we provide. And so that's a way to have very relevant answer in natural language with the LLM. Now, from all those pieces and example, I hope I convince you that sometimes what we want is a pure deterministic execution, like a pure function, to get today's date. We don't need an LLM for that, and we should avoid it. Sometimes we need an LLM function because we need some interpretation. We need we have some implicit language instructions that needs to be basically figured out. But most of the time, what you're interested in is a combination of both. And you want to do things step by step in order to ease things for the LLM and to augment, to increase your rate of success, because LLMs, as you may have seen, you understood, is something that is stochastic. So what you have a given rate of success, and you want you want it to be close to 100%. So that's what we do with LLM graph, where we organize function execution and LLM function execution in a flow. First, we're going to compute today value, which is a kernel function. We're going to generate day color based on some language instruction, just like we did before, providing a tool to this LLM function. And then we're going to take those results, day color and today, to generate, to pick the right value. And we want the answer to be a color. So we have two LLM function and a function here. This builds a graph object here, which basically works just like function and LLM function. We're going to evaluate it. We're going to inspect with information the flow it represents. So those are LLM nodes. They submit to LLM. Those are kernel nodes. They submit to the kernel. And you see that both of those outputs are used to generate this node prompt. Just like function, we evaluated the workflow, which is this object. Submitting day color, here generating the day colors, and here it returns, excuse me, the actual value. But in this, with the workflow, you can also intervene. It's very important to have human intervention in LLM workflow. So you can set, just as arguments, the output value of any node. This is assigning day color output to Monday, Tuesday, Wednesday is going to be red, Thursday, Friday, Saturday going to be green, Sunday blue. And you can query as a property the node you want to return, in this case, everything. You see that if I force this, it's going to only run today and current color, and it's going to adapt, deciding on Wednesday, which is red. And I can also decide that today is going to be Monday and inspect it, and oh well, it's going to be red again. Let's say it's a Sunday, and it's right. Oops. Let's do it again. With today being Sunday, hopefully it's going to return blue. So in this case, it's going to bypass the kernel execution. Today, C has been set to Sunday, and it looks like it picked the Sunday color here, which, oh yes, I haven't set anything for so Sunday color is this one. Let's look at this. Right answer again. Okay, so when we built LLM graph, we did everything in order to make it to favor efficiently. So we have the dependency in the graph are figured out automatically. If you have a sum node that does a sum and a square one that square the previous one, it figures out that this slot here is actually the key used here, and so it does the link properly. It figures out the A and B are not nodes, so it generates empty nodes with no computation to just host the input value. And at runtime, dependency are managed too. So it sees that if you provide the sum output doesn't need A and B, and it's going to generate the answer anyway. You can ask for only the square value. If you ask for the sum value, the square is not being computed and just return as the sum A plus B. All the LLM function nodes which don't have a dependency link can be executed in parallel. So here are two calls that I execute in parallel. You're going to see that call 2 and 1 are submitted in parallel and returning. And every LLM node can host a different configuration. So this one is the default one on OpenAI, and this one is the modified one submitted to Claude. So you can run each node to the model you like. Because LLM calls are usually lengthy, you can just ask to return a partial LLM graph and run the computation in several steps. And for those parallel evaluation to be possible, things are run actually under the hood asynchronously, and you can use LLM graph submit to have a task that doesn't block the kernel, and you can evaluate something before it's finished, and then returns the day color you've been assigned with the handler function. That's it. Just to convince you that it's powerful, here's a use case where 3 lines to kind of summarize Alice in Wonderland texts, which is first chunking it to split the text into something that can be accommodated to a small LLM, something you host locally, for instance. And then this chunk summary is summarizing every chunk. It's threading over the chunk to finally get the synthesis of all the chunk summary. So very basic workflow, but giving you a very efficient LLM submission for to generate this Alice in Wonderland summary, and similar to what those text summarize. And that's it. Thank you very much. I'm now going to check on question you may have asked if anything was unclear. So here is the first question. Why LLM graph does not support cyclic graph? That's technically the answer is quite simple. It's because in terms of dependency management, it was a bit harder in terms of corner case, and if we do it, we want to do it properly, make sure that everything is clean. So it's potentially for future version. And also, if you have, there is an interesting design issue. If you have cyclic like this, it's how do you handle the termination? If you're interested, just to mention before I move to the next question, if you're interested with just putting your hands on LLM graph objects, I suggest invite you to come to the hands-on about all those material in this afternoon. Another question: I just tried LLM synthesize with OpenAI, and I got an error message: incorrect API key provided. Well, yeah. Okay. So again, we are technically just serving as a proxy in this case. So if you want to use OpenAI with your account key and OpenAI rejects it, there isn't much we can do at our level. The only thing you can do to troubleshoot this is to make sure that the one on your account is the one here, and then you probably have to check your privilege with OpenAI. That's the issue with a provider, and that's probably also a reason to use use some built-in mechanisms such as LLM kits. So I don't think I can help much. Backpropagation briefly. Well, this is a bit out of scope, but yes, I can. That's so technically, if that's a neural network oriented question, it's when you train a neural network, how do you fine tune the weights? You fine tune the weights by computing the gradient in your neural network, and so gradient depending on all the weight value, and by moving one step in the gradient direction so when you train, you attach a loss to your networks. This is a cost value that's computed at the end of which basically telling you how good you are doing with the current value, output value. And you compute the gradients with respect to the weights of this value. You do one step in this gradient direction. Backpropagation is just one way to organize this gradient computation in a technique, in a performant way, computation-wise, which is usually your network is more shallow at the end, and when you do the composition rule, because all those neurons are stacked together, you get less matrices multiplication if you propagate your gradient from the tail of your network that's starting with the input. That's what backpropagation is about. I don't see any more questions, and I think we are just reaching the end of this talk. I thank you very much for coming here, and I know it's dense. I hope it was clear enough.